This question arose in connection with a new chapter from the 10-year anniversary edition of the book, What If?, now available both online and in print. At the end of the video about laser pointers, we gathered a mass of lasers with a total power of 2 times 10 to the 24th watts, which not only illuminated the moon, but also violently ejected it from its orbit around the Earth. We decided that this power is enough, but why not try something even more powerful? A laser with a power of 2 times 10 to the 24th watts is impressive. When we turned it on, it made the surface of the moon facing Earth significantly brighter than the sun. It's impressive, but we can do better. In the universe, there are deadly rays that make our lunar laser look like a handheld laser pointer. Gamma bursts are what we call very high-energy photons of electromagnetic radiation. When you see the diagram of the electromagnetic spectrum, gamma rays are everything more energetic than X-rays, literally going off the chart at the upper edge. They arise from high-energy events, such as nuclear explosions. Gamma bursts occur when something very bad happens to a star. When massive stars collapse, their cores succumb to the destructive force of their own gravity, releasing a huge burst of energy and tearing the star apart from the inside. For reasons we do not fully understand, these explosions often produce jets shooting along the poles of a collapsing star. These streams can travel across much of the universe, and when Earth aligns with one of them, we see it as a flash of gamma rays from deep space. We did not know about gamma bursts until we launched a satellite to observe gamma ray flashes from nuclear explosions on Earth, and were surprised to see flashes coming from all over the rest of the universe. The peak power of gamma ray bursts can reach about 10 to the 44th watts, which is much more powerful than our laser array. To achieve our own deadly beam with a power of 10 to the 44th watts, we need to provide each person on the moon's side facing Earth with a laser power of 2 to the 34th watts. That is, every person would need a laser 10 billion times more powerful than the final combined laser that violently ejected the moon. This is an unlikely scenario, and it won't work for reasons we will discuss later. But first, let's consider what we could do with such a beam. We needed to carefully focus it, as laser beams disperse with movement. The minimum angle of dispersion depends on the size of the beam source. For laser beams emitted from 2-meter-wide lenses, the limit is about 0.1 angular seconds, or 0.3 of a degree. The formula for the limit of a laser beam strangely resembles the formula used to determine the maximum resolution of telescopes, like the Hubble, because in a sense, a telescope is just a deadly beam working in reverse. The Hubble has a mirror with a diameter of 2.5 meters, and its angular resolution is slightly less than 0.1 arc seconds, similar to the angular limit of our 2-meter laser. The laser array from the original chapter was quite powerful, but not particularly narrow. If he were focused into a beam like the Hubble, he could theoretically bake the surfaces of planets in our galaxy. A deadly beam of 10 to the 44th watts would be much worse. If we focused it to the limit of diffraction, it could reach targets far beyond our galaxy, burning the surfaces of planets at distances of up to 5 or 10 billion light-years. But don't rush to buy a laser with a power of 10 to the 44th watts. At cosmic energy levels, ordinary optics cease to work. For example, if a beam is powerful enough, it can exert gravitational attraction on itself. A photon carries energy, and energy creates gravitational fields. For ordinary light rays, this is insignificant, but for a laser with a power of 10 to the 44th watts, the photons at the outer edge would experience an acceleration of over 10 g towards the center of the beam. However, physics has one more surprise in store, which ultimately sets an upper limit on how powerful lasers can be. If a beam of light becomes too bright, space itself stops being transparent. If you pack enough laser energy into a small enough space, quantum mechanics predicts that strong electromagnetic fields will lead to the spontaneous creation of particles and antiparticles. These particles, mainly electrons and positrons, will intercept some of the laser energy, leading to the creation of even more particles. For laser power densities above approximately 10 to the 26th watts per square centimeter, this process is expected to be cascading, completely halting the progress of the laser and setting an upper limit on how much power our beam can have. In the end, it turns out that physics is not mathematics. You can always find a larger number, but you cannot always create a more powerful laser.